Okay, so welcome back to another video. In today's video, we have the following question from the Putnam Exam from 2015. So this is A1, so this is the first question that's offered during the daytime. So we let A and B be points on the same branch of the hyperbola x times y equals 1. Now suppose that P is a point lying between A and B on this hyperbola such that the area of the triangle APB is as large as possible. So show that the region bounded by the hyperbola and the chord AP has the same area as the region bounded by the hyperbola and the chord PB. So I know there's just a jumble of words, and then we only see just the one equation, x times y is equal to 1. And we also given the condition that suppose that we have a point P between A and B that lies on that same hyperbola, and such that the area of that triangle is as large as possible. So just reading this on its own, it might be a little bit confusing, but how about we demonstrate this visualization with a diagram? Okay, so here we have our hyperbola x times y is equal to 1. In other words, if you just want to rewrite this equation in terms of just y on its own, it's basically just y is equal to 1 over x. And here we have our 2 points A and B. They lie on this same hyperbola. But before I go further, I would also like to put in a clarification. Rather, we assume without loss of generality that A and B are on the hyperbola, but also specifically the first quadrant of our coordinate system. And also we also let that it's the x coordinate is of A is smaller than the x coordinate of B. So now we're also given that we want to suppose that P is a point lying between A and B, lying in this hyperbola. And the thing is, we're also given that APB is the area of that triangle is as large as possible. So if we think of this, if we say P were to lie anywhere between A and B, right? So maybe P could be here or P could be there. So if we were to sketch out a triangle of P, of that point P, then you'll notice that the area of that triangle is small. Same thing for over here. So any points B that is relatively close to either points A or B, the area of that triangle is small. If we want this triangle to be as large as possible, then what that means is that if I were to say, for example, well, not really for example, say the way we're going to do this is that if I sketch this line segment from A to B, so like so with the line segments over here, and if we want the area APB to be as large as possible of its area, that actually means that the perpendicular distance of P to the line segment AB, that also has to be maximal. So the perpendicular distance, meaning that the line segment P over here, and if we draw a line that actually forms a 90-degree angle over here because it is perpendicular, then also means that I have to sketch out of course our chord from AP and PB. So let's see, we have AB or PB, and then the other one is AP, like so. Okay, so here's our triangle over here. So now that means perpendicular distance, but that also has to imply that the slope of line segment AB has to equal to the slope at the point P. So here we have our slope, like so. I'll just represent the slope in dotted lines. So that means the slope of line AB has to equal to the slope at the point P. It's not the best drawing, but you get the picture. Okay, so we have this description. So now, what I'm going to do is now, of course, we have that the hyperbola is x times y is equal to 1. So how about I write this as a function of y? So y is equal to 1 over x. So y equals 1 over x. And let's also define our coordinate points. So here I'll let capital A. We'll let that equal the x coordinates, just lowercase a, for example. And if we put in the y value, so that means it'd be just 1 over a, or I'll write this as a inverse. Same thing for our coordinate, our point B, the coordinate b inverse. And for the point P, we'll call that P, and then the y coordinate is p inverse. As mentioned, if we're going to calculate the region of the bound of the hyperbola and its respective chords, so we have to basically calculate the regions over here, this small region here and this small region here, and show that those areas equal to each other. But in order to do this, we would also need to calculate the slopes, but also find where the bounds in between when we're doing this sort of integration. So we'll do this one by one. So first, I'll take the derivative of our function, our hyperbola 1 over x. We'll take that in respect to x and evaluate that at the point p, x equals p, and then I'll also calculate the slope of that line segment from line AB. So doing this, so we get d over dx at the point xp, just 1 over x, and if we set that equal to the change in y and change in x, that would be b inverse minus a inverse, and then that's just divided by b minus a. Now, if we can continue writing this further, I take the derivative of this, that's just using the product rule or quotient rule, and then we get that this is negative 1x squared, and then evaluate at the point p. Of course, now over here, I'll actually just rewrite I can rewrite this and find the common denominator. So let's see, 1 over b and then minus 1 over a. So that means we have a minus b, and then we divide this by ab. And we'll just subtract that, or divide that with b minus a. And of course, if I can continue writing further, this will be a minus b, and then this will be divided by ab, using the product with the whole division. So this is just 1 over b minus a. And if I can continue further, these two cancel out, but that just means that we'll have a negative. So this will be negative 1 over ab. So that's the right hand side done. So now we have to calculate this. So we have that this is just negative 1, and then evaluate for x equals p, that'll be p squared. Set that equal to negative 1 divided by ab. And then if I were to solve this for p, so at least we know what the x coordinate at the point p is. So let's see, so we have negative ab. If I just do it like the cross multiply, so just get rid of the fractions. So again, negative p squared. Divide this by 1 by both sides, so we get p squared equals ab. I just wrote p squared first. It's the same thing. The equality still preserves. And if I take the square root, so we don't really need to worry about the negative square root, since we're really just focusing on just the first quadrant. So the positive x values. So we get that p is equal to the square root of ab. And so now the thing we want to do now is we want to show that the regions bounded by the hyperbola is the area with those chords are equal to each other. So now this is where the calculus comes in. So now that we know that our coordinate point p, the x coordinate, that would be the square root of ab. So if I take that y coordinate, so if I find its y coordinate, just plug this back here, we get that this is just the square root of ab inverse. Now, continuing further, what I'm going to do is the way we're going to calculate these integrals. So of course, we're going to need our bounds. So what I'm going to do is I'm actually going to draw a little extension over here. So we have that our coordinate a, the x value is that it's the lower bound there. So let's see if I draw this down below. Okay, and I'll call this point C. And if I extend this line over here, we'll call the point over here D. And then I'll draw this down below over here. We'll call this E. So now it's just finding the area. So what I'm going to do is, in order to find like the area of this little region bounded with the chord and the hyperbola, what I can do is that I can actually find the area of this trapezoid over here, and then I'll subtract that with this inner piece over here. So all we're left with is just this region. So we're finding two areas and then subtracting to each other, and then we're going to use that same method for over here. So really the general formula, what I'm going to do is, let's see, I'll call this area over here. So the first thing I want to calculate is I want to calculate this area. So I'll write it as this. So the area, this thing's running out of markers, so I'm just going to go back to the orange. So I'm going to write this as the area. This is bounded by, I'll call this the bounded by the hyper, I just abbreviate for hyperbola, and the chord AP. So really what that equals to is that we need to calculate the area of our trapezoid. So this is trapezoid ACDP. And then I'm going to subtract that with this area over here, not including this little chord, because that's the one we want to show. So our bound really is at the x-coordinate. The lower bound would have to be at a, and then its upper bound would have to be ab, the square root of ab of our function 1 over x dx. And then that's not hard to show. We know that our area of a trapezoid is we take the addition of the two heights, divide that by 2, but also multiply by its height, which is the distance between point C and D. So, okay, so now calculate the trapezoid. So we have the square root of AB inverse. I had this with A inverse. I'll just divide this by 2. Then I multiply it with the distance from C to D. So this will be that x-coordinate where that P meets is supposed to be the square root of A, square root of AB. And I subtract that with A. And then I subtract with finding the integral, so we know that the antiderivative of 1 over x is just the natural log of x. And then we find it with our bounds between square root of AB, or a, and then square root of AB. Okay, so next, now I can just simplify this expression further. So I'll write this as 1 over square root of AB plus 1 over A. And I'll just divide this by 2. Then multiply with the distance, the square root of AB minus A. Then continuing further, then if we do the simplification, we'll get that this will be A plus the square root of AB. And then we divide this by, so common denominator, A times the square root of AB. So multiply this by, or divide by 1/2, whichever you want to put it. Then multiply with the square root of AB minus A. So you see over here, we do the multiplication. This is actually just a difference of squares. Then we get, this is A square, or rather, this is supposed to be A times B. That's the first. It's supposed to be A times B, then subtract with A square. And I divide this by 2AB, then times the square root of A, times the square root of AB. And then I can subtract this with, evaluate our bound. So this is the natural log of the square root of AB, then subtract with the natural log of A. Okay, but then now if I simplify even further, then what I can do is I can factor out an A, and then the A's will cancel. So then I'll just be left with B minus A. Then divide this by 2 times the square root of AB. And then subtract with, okay, so we use our natural log rules. So this is the natural log of square root of AB. So in other words, I can write this as 1/2 ln of A, then plus 1/2 ln of B minus ln of A. I do the subtraction, so we have 1/2 ln of B minus 1/2 ln of A. And if I perform that subtraction, we get, and then rewrite everything out as a single logarithm, then we get that this is just the natural log of the square root of B divided by A. Okay, and that's one area found. So now we have to find the other area. Okay. So now the last thing we need to show is to find this area. So of course we're going to use the same strategy just like before. So now we have to calculate the area bounded by the hyperbola, just abbreviate that, and PB. So now that means I have to calculate the trapezoid over here. So this will be PDEB, and I subtract that with our integral. So we're just calculating the integral from our 1 over x function dx, but then our bound would have to be from the square root of AB, and then b, that's our upper bound. Okay, so now performing this, so same strategy. We add the two basis length, multiply by its height, and then divide by 2. So let's see, so this will be b inverse, and then plus the square root of, how do you put this in parentheses? This will be the square root of AB inverse, and then now we just divide this by 2, then multiply with the distance from D to E, which is just B, subtract with the square root of AB. And now we know that the antiderivative of 1 over x is just ln of x. And we evaluate this from the square root of A times B to B. So now I just perform the necessary calculations. Well, not really calculation, but simplification. So this is 1 over B, and then we add this with 1 over the square root of AB. This is still divided by 2. Then we multiply this by, of course, with the distance. I'm just taking it slow. We're just doing one tiny step at a time. So then now we do the butterfly effect. This is just the square root of AB, and then plus B. Then we divide this by 2, or excuse me, multiply the denominator. So this will be B times the square root of AB multiplied by 1/2. And of course multiply with B minus square root of AB. But of course this is still the difference of squares when I do the multiplication. So we would get that this will be B squared minus A times B. And then subtract with 2 times B times the square root of AB. And of course we evaluate from ln of B, and then subtract that with ln of the square root of AB. And we're almost done. So now, just skipping a couple steps, of course, I can factor out a B from here, and then the B's will cancel. So then we just have B minus A, and then divide by 2 times the square root of A times B. And our last step, of course, is to use the natural log rules. So we have ln of B minus ln of the square root of AB, which is just, over here, this is 1/2 ln of A plus 1/2 ln of B. Distribute the negative, so the B will become negative, so we have positive ln of B minus 1/2 ln of B. So it's positive 1/2 ln of B, and then subtract with 1/2 ln of A. So then, therefore, that combining this under a single logarithm, we have that this is just the natural log of the square root of B divided by A. And would you look at that? You see that we have two areas that actually share the same value. So therefore, this area enclosed with the our hyperbola function and the chord AP is equal to this area, while this area of our 1 over x function and then with the chord PB is also equal to this function, equal to this value. So we see that these two share the same value. These two regions are equal to each other, and thus concludes the proof. All right, now that's pretty cool if you ask me.